Okay, so now we're going to talk about gradients, divergence, and curl. First, the definition of a gradient is given by the following. We have this operator called the Nabla operator or the del operator, and it's denoted as a vector acting on some kind of scalar field, which is denoted by v. And in this case, v is given as x, y, and z. So this means that we have the partial derivative of v with respect to x acting in the direction of x plus the partial derivative of v with respect to y acting in the direction of y and the partial derivative of v in the direction of z as given below. Now, intuitively, what this tells us is we're asking is what is the rate of change in all three directions? Now, previously, we looked at partial derivatives, which what this tells us is what is the slope in the direction of x? Slope in x. But when we're talking about a gradient, we're talking about generally what is the slope throughout. And this introduces to a lot of things, such as directional derivatives, and just in general asking where is the rate of greatest, or where's the greatest descent or ascent. We can cover this a little bit more, but we have to move on to divergence and curl. So divergence is similarly defined, except it is acting on two vectors. So we have a vector given by the Nabla operator and some vector field f, which is also dependent on x, y, and z. This, as it's a dot product, gives us a scalar result given by the following: del f del x plus del f del y plus del f del z. What this is essentially telling us is that given any kind of whole, that we can, if this divergence was for whatever reason greater than zero, then it's actually sourcing outwards. And we can see that this is very useful for talking about electric fields or electric field distributions when we're talking about either a line of charge or just a point charge. Now, if it's for whatever reason less than zero, then it's sinking. And this could correspond to an electron whose electric field is sinking into itself from a proton that's infinitely far away. In the event that this is equal to zero, it's neither sinking nor sourcing. And we enter a kind of net neutral source for at least this part. Lastly, I want to then talk about curl. Curl is defined similarly to divergence, except we use this symbol to denote a cross product between the two. Now, a cross product between two vectors gives us another vector. And in this case, this is given by the determinant of the following. So in the direction of x, in the direction of y, and in the direction of z, we have our partial with respect to x, our partial with respect to y, our partial with respect to z. Then we have f1, which is our first coordinate, f2, and f3, just to keep it more general. Now, there are a few ways to go about calculating the determinant very quickly, but the most conventional way is just crossing out the row and column and taking the determinant of a lower order matrix or a subdeterminant. So in this case, we have in the direction of x, ax, which is given by the partial of f3 with respect to y minus the partial of f2 with respect to z plus, or sorry, it goes into an alternating format. So it should be minus ay. And so from here we cross this part out and we take the determinant of the following. So we have partial f3 partial x minus partial f1 partial x. And then we have then az denoted by the following. Cross these this row and column out, and we get the determinant of this. Gives us partial f2 partial x minus partial f1 partial y. Now, intuitively, because this operation is a cross product, what we are asking is how does this new vector created by the multiplication of two other vectors, what does that give us? Well, when we're discussing about curl, we're usually discussing about rotations. And this would be very useful also when we're talking about electromagnetism, such as in the case of Maxwell's equations, just to kind of refresh on that. So as such, this gives us all three. And in the next couple of videos, we're going to explore how we can use gradients, divergence, and curl, and to do at least a few problems. Okay, have a good day.